Welcome to Ask and Learn.
We're asked to show that there is no finite-state automaton with three states that recognizes the set of bit strings containing an even number of ones and an even number of zeros. So to do this, we will use a proof by contradiction. So suppose that such a machine exists. With a start state S0 and two other states S1 and S2. Now consider the empty string. Lambda contains an even number of zeros and an even number of ones. So it follows that lambda is recognized by the machine. Therefore, or I should say lambda is in the language, and therefore lambda should be recognized, and it follows that S0 must be a final state. Now, the string 0 does not contain an even number of zeros. So it follows that 0 and 1 does not contain an even number of ones. So these two strings must not be recognized by the machine. It follows that there must be transitions from S0 to some other state for each input. Now, we have that both transitions from S0 cannot lead to the same state S as a zero transition. From that state, S would lead to an accepting state. So to prove this, suppose that both transitions from S0 with the two inputs move to same state S prime. Then it follows that zero, zero must be recognized so it follows that transition from S prime to S0 again, so the transition from S0 with input 0 must be recognized. So this state must be final. However, it follows that the string 1, 0 would also be accepted then. Since again we're moving from S0 to S prime to this next state. So it also end up at a final state. But this is a contradiction, since 1, 0 contains an odd number of ones and an odd number of zeros. Therefore, it follows that both transitions from S0 cannot lead to the same state S prime. So let's suppose that the input 0 leads to a transition from S0 to S1. And therefore it follows that the input 1 leads to a transition from S0 to S2. Now again, the strings 0 and 1 are not recognized. So S0, okay. So that S0 and S2 are, not S0, I mean S1 and S2 are not final states. So the only final state is S0. However, we also have that 0, 0, and 1, 1 need to be accepted. So it follows that there's a transition with input 0 from S1 to S0. And there is a transition with input 1 from S2 to S0. However, the string 0, 1 must not be recognized. Because it only contains an odd number of zeros. So it follows that, well, our first bit is a 1, so we go to state S2. Our second bit is 0, so it follows that there is transition or I guess I should say the transition with input of 0 at S2 is from S2 to well, in this case either I guess I could flip this around. So consider instead the string 1, 0, my mistake. And so it follows that the transition with input 1 at S2 instead of S2 actually at S1 is from S1 to itself or from S1 to S2, but not from S1 to S0. Now suppose that there is a transition from S1 to S2 when the input is 1. Well, then it follows that the string one, 1, and then 0 must be accepted. So if this is the case, then it follows that the string 0, 1, 1 will be recognized by the machine. But this contains an odd number of zeros, so this is a contradiction. Therefore, it follows that there is a transition with input 1 from S1 to itself. However, then it follows that the string zero, 0, 0 because there's a transition with input 1 from S1 to S1, then there's a transition with input 0 from S1 to Then it follows that the string 0, 1, 1 would be recognized by the machine, because with the input of 0, we move from S0 to S1. With the input of 1, we move from S1 back to itself. And then with the input of 0, we move from S1 back to S0, which is a final state. And again, we see that this string only has 1, 1, which is an odd number of ones. And this is a contradiction. However, at this point, we've considered both forms of transitions with input 1 from S1. And this implies that our initial assumption that such a machine would exist is incorrect. So no such machine exists.